All right, so far we have obtained invariant subspaces for AES, and we use this to obtain weak key truncated differentials or invariant subspace attack distinguishers for AES. So those distinguishers were longer than traditionally obtained distinguishers. Then we combined these invariant subspaces with the subspace trails and obtained longer distinguishers for AES, like for 6, 7, 8, and 9 rounds of AES. But this time we obtained a multiple of n property. Here in our examples, n were either 128 or 2 for the longest distinguishers. But again, now the question is, once you have a very long distinguisher, can you turn it into an attack? But again, as we mentioned before, it is hard to turn these into attacks on more rounds due to the time complexity upper bound. Recall that if you are focusing on 2 to the 32 weak keys, so if you start with the assumption that the user chose one of the keys from this space, then an exhaustive search attack would require 2 to the 32 encryptions. So if you want to have a better attack, then you have to do less operations, but we are working on many data and we need to perform a lot of encryption and decryption operations. So it is not possible to turn these into attacks on longer rounds, but we can turn them into chosen key distinguishers on more rounds. So this leads us to the idea of chosen keys or open key distinguishers. So let's look at this first. Goal of an open key distinguisher is as follows. Differentiate between a block cipher and an ideal cipher by generating plaintext ciphertext pairs which exhibit a rare relation, even for a small set of chosen keys or even a single chosen key. Steps to usually set up a chosen key distinguisher are as follows. Describe the rare property. In our case, this is the multiple of n property. Show that it can be efficiently constructed for the block cipher, instantiated with a chosen key using an inside-out approach. Argue or prove in some model that any generic method is less efficient or has low success probability. So our aim is to show that a property of the cipher has different probability compared to a random permutation, but that rare property actually is valid once a key is chosen from a very small space, or maybe it only works on a single key. So in this case, you know the key. So you can also think about it like this. In cryptanalysis, you are actually trying to capture the secret key. So in this scenario, we actually know the key, or we choose it from a very small space and try to obtain a rare property and show that it is really a rare property, so that it's hard to construct for a random permutation or an ideal block cipher. So let's look at some examples. For the single key chosen key distinguishers, so by single key we are assuming that you capture ciphertext, or so somebody is using AES and uses only a single secret key. So we call this a single key scenario, which is most of the time what we are trying to attack. So in the single key scenario, there are some distinguishers up to 8 rounds for AES 128 or 9 rounds for AES 256. These chosen key distinguishers choose plaintext pairs so that the XOR of the plaintext are in the diagonal. So the difference is in the diagonal space, and you observe the difference in the mixed columns in the ciphertext. And in the related key scenario, we assume that you use AES for using a single key, then you change the key and you continue using AES with the second key, but we know the relation between these keys. So it is called a related key scenario. So for this kind of scenarios, there are up to 9 round distinguishers, chosen key distinguishers for 9 round AES 128, and there are full round, that is 14 round AES 256 chosen key distinguishers. So you can look at the related papers. This one is from, I think, from Biriko Kaurotovic and Ivica Nikolic, if I'm not mistaken. So we are not focusing on the related key in this talk, but we are focusing on the single key scenario. So we are focusing on obtaining a distinguisher where a single secret key is used. So our aim is as follows: find a set of 2 to the 64 plaintext ciphertext pairs where ciphertext is obtained by encrypting the plaintext R rounds under the secret key K, such that if you choose any combination of the bytes, the number of different pairs of plaintext that are equal in the ith byte for every I in this subset L is a multiple of 2. And for every j, the number of different pairs of ciphertext that are equal in the jth byte for every j in this set is a multiple of 2. So you are fixing the bytes in the input, which we call I, and you are fixing the bytes in the output, which we call j. So we are trying to find 2 to the 64 plaintext ciphertext pairs where the collisions on these bytes are a multiple of 2. Similarly, we can use the multiple of 128 property, but this time the collisions on the plaintext sides are on the diagonal, and on the ciphertext side it is on the inverse diagonal. So by using this method, using the distinguishers we obtained so far, this multiple of m properties, we can construct up to 9 round AES 128 chosen key distinguisher and 12 round AES 256 chosen key distinguisher for 2 to the 32 weak keys. And actually for a single key, we can find a distinguisher for the full AES 128, which is 10 rounds, and full AES 256, which is 14 rounds. But for a single key, you already know the key, so obtaining a distinguisher might not be that interesting. So how the idea works. So consider 2 to the 64 tags. We represent them with Ti in our invariant subspace and choose the fourth round key as the weak key. So you start with your invariant subspace. We know that if you decrypt one round backwards, you obtain a coset of the invariant subspace. And any coset of invariant subspace turns into a multiple of m property if you decrypt it 3 rounds backwards. So this is how you obtain the multiple of m property on the plaintext side. But if you go on the forward side, if you encrypt 2 rounds of AES, you obtain a coset of AES. Remember that we already done this in the previous videos. And if you encrypt it 3 more rounds, you obtain the multiple of m property. So as you can see from here, we decrypted backwards. So we decrypted 4 rounds backward, and we encrypted 5 rounds on the forward direction. So this is how we obtain a 9 round distinguisher. So given 2 to the 64 random ciphertext plaintext pairs, the probability that all previous events are satisfied is this, which is a very small number, as you might imagine. So indeed, for the multiple of 2 property, we have a lot of possibilities because we can choose which bytes that we want to see the multiple of 2 property. And for the multiple of 128 property, we can choose the diagonals and inverse diagonals. So there are many possibilities. But so we can easily construct this distinguisher. The question is, can somebody else construct such a distinguisher too? So if you are given 2 to the 64 plus 2 to the 13 different plaintext ciphertext pairs, then there are 2 to the 64 pairs of text that satisfy the required property with good probability, higher than 95%. However, one must construct all of the possible combinations of the pairs from these plaintext ciphertext pairs, which is a very huge number. So once you do it, you also obtain such a distinguisher for any ideal cipher. But again, we think that this requires a lot of work. Of course, some you might argue that maybe there is an easier way to do it, but since we don't know it, it is hard to argue about the quality of chosen key distinguishers. So we evaluated other strategies in our paper. We conjectured that there is no efficient strategy to fulfill the required simultaneous multiple of n property, for which the cost is less than 2 to the 64 computations. So in our case, we just perform 2 to the 64 computations and obtain this distinguisher. But for an ideal cipher, we conjecture that it is not possible to do it with less than 2 to the 64 computations. So if we give it in a table, to the best of our knowledge, one of the best chosen key distinguishers belong to us. Again, we can increase this number to 10 and this to 14, but then we have to argue how hard it is for an ideal cipher and so on. So this is why we stopped at this. And at this part, this is on related key setting. We are doing it for the single key setting. So to the best of our knowledge, these are the best results obtained for AES so far. So there's a 10-round AES 128 chosen key distinguisher by Gilbert, and we didn't include it in the table because this distinguisher is arguable, and it is argued in the paper by Gress and Lefberger titled Revisiting Gilbert's Non-Key Distinguisher. So actually the idea is as follows. In this distinguisher, you obtain the distinguisher by performing some partial encryption operations. So you have to guess some key bits or perform some encryption operations to see if the result is observed or not. So it is not directly obtained by looking at the plaintext and ciphertext. So question is, does a property that requires calculation of intermediate values be called a distinguisher? My person is currently no. This is why we didn't include the Gilbert's distinguisher, but again, maybe in the future, somebody might convince me that this is not the case. So I'm open to any suggestions. So my aim was to, in this talk, to show you there are many different areas in cryptanalysis, and just by trying to obtain some distinguishers for AES, we covered invariant subspaces, subspace trails, weak keys, chosen key distinguishers. So this was just to give you the general idea about these concepts and show you how they work in practice.